to highlight some of the guidelines that we discussed at the end of the last problem, when you're trying to solve for an applied minima or maxima problem, the first thing you would want to do is identify all the given quantities and all the sketches and all the quantities to be determined. If you're able to make a sketch, it's a good idea. That'll oftentimes help you to realize the situation that you're in and to maybe set up your variables. The next step would be to write a primary equation for the quantity that is to be maximized or minimized. From there, the goal is to reduce the primary equation to being that of a single variable. This oftentimes requires use of that secondary equation, which we refer to as a constraint equation. Solve the constraint equation for one of the other variables, and then you can substitute that into your primary equation to reduce it to a function of a single variable. The next thing we should do, and we didn't do this on the last problem, although we should have, was to determine the feasible domain of the primary equation. That is, determine the values for which the stated problem makes sense. If you go back to that last problem, for example, we know that x would have to be greater than 0. So when we're looking at that function v of x, realistically, x has to be greater than 0 because it's a physical length. If x is not greater than 0, then you only even have a box in the first place. But then we also know that v of x2 has to be greater than 0. Technically greater than or equal to 0. If we go back and look at the equation expression we had for v, and the form I'm going to use is going to be the following form. V was 108 x minus x cubed divided by 4. This has to be greater than or equal to 0. If I multiply both sides by 4, I get this inequality, 108x minus x cubed has to be greater than or equal to 0. You can factor out the x. For this inequality, we know x has to be greater than 0, which would mean that this quantity would also have to be greater than 0 for this inequality to be satisfied, which would mean that we need 108 minus x squared to be greater than or equal to 0, or 108 to be greater than x squared, which means that the square root of 108 would have to be greater than or equal to x. So when we talk about, what would the feasible domain be, it's 0 would have to be less than x, which would have to be actually technically less than the square root of 108. And the reason why x has to be less than the square root of 108 is that if x was equal to 100 square root of 108, then that y component would be equal to 0, but we also needed the height of the box to be non-zero to have a realistic box. Okay. So if you just kind of take that v function out of context, it was a polynomial, so it would have domain all real numbers. But given the physicality of our situation, the feasible domain, in other words, the domain for which that function would make sense to us, would be for values of x between 0 and a square root of 108. Okay. From there, you would determine the desired maxima or minima value by using the techniques we found in previous sections. Take the derivative of your single variable function, find the critical numbers, use either the first or second derivative test in order to determine whether you get a maximum, minima, or neither. And then you should also check at the endpoints to see if you get any extrema perhaps at the endpoints as well. Let's take a look at example 2. The question says which points on the graph of y equals 4 minus x squared are closest to the point 0, 2. So we want to minimize a distance here. So which points are closest? So we're looking for a minimal distance here. And let's suppose that we have a generic point on this curve. Let's call it x comma y. We can find the distance to the point 0, 2 using the old school distance formula from college algebra. The distance would be equal to the square root of the difference in the x values squared plus the difference in the y values squared, and then we would take the square root of that. This would produce x squared plus, and I'm going to leave this in factored form for right now, y minus 2 squared. So this is the expression that we want to minimize. And in terms of the minimization, it's not just any x comma y. It's not just any ordered pair here. It's the ordered pairs that are on the curve, y equals to 4 minus x squared. So in a sense, that's kind of like our constraint equation. That's the relationship that x and y have to satisfy. Well, what that will give us is an opportunity where what we can do is everywhere you see the expression for y in our distance formula, we can replace y with 4 minus x squared, and that will give us a function of a single variable. So d is equal to the square root of x squared plus 4 minus x squared minus 2 squared. D is equal to the square root of x squared plus, and on the inside here, this is going to be 2 minus x squared squared. We can, of course, go ahead and let's simplify this a little bit more. D is going to be equal to, we have the square root of x squared. If I expand everything on this other term, you would have 4 minus 4x squared plus x to the fourth. And now let's go ahead and write it in standard form. So d is equal to the square root of x to the fourth minus 3x squared plus 4. So we have our function of a single variable. We can now go ahead and try to find our critical numbers by taking the derivative. Sometimes for this particular problem, there is a shortcut trick that some people will use, which is a little bit more of an advanced technique. And that's that we're trying to minimize this d value, which is essentially minimizing the square root of this thing. It simply would boil down to minimizing the quantity on the inside. So you could kind of focus on just the x to the fourth minus 3x squared plus 4 thing, but let's work with it in its full generality, since I know we're all able to do that. So I'm going to come up here, giving us some more room. Let's write out the expression for d. So the distance here is equal to x to the fourth minus 3x squared plus 4 raised to the 1/2 power. We want to take the derivative with respect to x. This should involve a chain rule, so it's going to be 1/2, reduce the power by 1, leave the inside function alone, and then from the chain rule, we need to multiply by the derivative of the inside function. That would be the following. It's going to be 4x cubed minus 6x. So the derivative with respect to x is equal to, and I can actually kind of distribute to make life a little bit easier. Let's take this 1/2 and distribute it into that second quantity, because that will reduce it. We get 2x cubed minus 3x, all divided by the square root of x to the fourth minus 3x squared plus 4. So we have our derivative. The next thing we want to look for is our critical numbers. So we would want to see where is the derivative equal to 0. If I set this function equal to 0, we would get the following. 2x cubed minus 3x, all divided by the square root of x to the fourth minus 3x squared plus 4 equals to 0. Clear fractions by multiplying both sides by the square root. We would get 2x cubed minus 3x equals to 0. We can solve this by factoring out the x. We get 2x squared minus 3 quantity times x equals to 0. We get x equals to 0. 2x squared minus 3 equals to 0. Add 3, divide by 2. X squared equals 3 halves. And I'll leave it like this, but we're going to get two solutions here. X equals plus or minus the square root of 3 halves. So altogether we have three critical values. Negative square root of 3 over 2, 0, and positive square root of 3 over 2. We would now want to use either the first derivative test or the second derivative test in order to see whether or not any of these critical numbers produce maximums or minimums. And actually, kind of getting ahead of the game a little bit, we also should see where the derivative is undefined. So what about those second types of critical numbers? So where would dx be undefined? Well, to answer that question, you would need to solve where is x to the fourth minus 3x squared plus 4 equal to 0. That's solving a fourth degree equation. It's reducible to a quadratic, so you could use that technique. You could also use technology to graph it, to see what the graph would look like. But it actually turns out that that thing will not have any solutions. So x to the fourth minus 3x squared plus 4 is never equal to 0, and therefore we don't get any critical numbers of the second type. So let's evaluate our critical numbers to see whether or not we're going to get maximums or minimums here, or perhaps neither. To do so, I could use either the first derivative test or the second derivative test. In terms of the second derivative test, it's convenient, but that would require us to take the derivative of this expression, dx, which is not going to be the most convenient expression in the world. So let's go ahead and just use the first derivative test on this one. It's good practice. So I'm going to do a number line. I'm going to plot my three critical numbers. They are negative square root of 3 over 2, positive square root of 3 over 2, and then we also had 0. Those three critical numbers will divide the number line up into 1, 2, 3, 4 different regions. And now what we're going to do is the method of test points to determine the sign of the derivative in each of those regions. In order to help me find the test points, we would probably want to know the value of those critical points. The square root of 3 over 2 is approximately about negative 1.2. So this is about negative 1.2. So for example, that would let me know that a good test point I could use in region 1 would be the test point x equals negative 2. We would take and plug negative 2 into our derivative. The derivative evaluated at negative 2. This would be 2 times negative 2 cubed minus 3 times negative 2, all divided by the square root of negative 2 to the fourth minus 3 times negative 2 squared plus 4. Let's go ahead and evaluate this one. So when I work it out, I get approximately negative 3.5, which is going to be negative. So in region 1, dd dx is less than 0, which means there the function is going to be decreasing. I'll kind of skip to the chase here, but if you do a test point in region 2, for example, negative 1 would work great there. D dx evaluated at negative 1, guarantee when you work it out that should be greater than 0. So d dx is greater than 0, which means that the function is increasing. In region 3, we can use the test point x equals to 1. If you calculate d dx evaluated at 1, that should be back to being less than 0. Which means the function is decreasing. And a good test point to use in region 4, we could use x equals to positive 2. If you evaluate the derivative at positive 2, it's going to be greater than 0. So in region 4, d dx is going to be greater than 0, which means that the function is increasing in region 4. Altogether, let's kind of take inventory of what did we find. Well, at our critical points, we do have the following information. At the critical number negative square root of 3 over 2, the function went from decreasing to increasing, so that will produce a minimum value. So we have a min at x equals negative square root of 3 over 2. Notice we do have a relative max at 0, where the function goes from increasing to decreasing, but going back to our original problem, our goal is to minimize this distance. We do have another min, however, at the square root of 3 over 2, because the function goes from decreasing to increasing there. So we have another min at x equals square root of 3 over 2. We should now go ahead and plug in these values into the function to see what points we get. At negative square root of 3 over 2, if I plug this into the function y, so when x is negative square root of 3 over 2, be squared. The y-coordinate is going to be 4 minus 3 halves. And then 4 minus 3 halves, if we get common denominators, that will be 8 halves minus 3 halves would be 5 halves. So we have a min at the point negative square root of 3, 2, 5 halves. And if you plug that same, not the same, but if you plug the other critical number in, because the function is even, you're actually going to get the same output. After all, it doesn't matter really whether I have a positive or negative here, square root. Once you square it, you're still going to get 3 halves. So the other point would be square root of 3 over 2, 5 halves. It might be worth asking, we should probably find, like, what is that shortest distance? Here it just said which points on the graph are the closest, and we found them. The 2 points, and we found 2 of them, and it makes sense due to symmetry, that there should be a solution here and a solution here. These are the 2 closest points to the fixed point 0, 2. Also, if we look, we do see the fact that we do get a relative maximum at 0 from our one critical number. If you look at, let's suppose, any ordered pair in this open interval containing 0, from negative 1 to 1, this point at 0, which would be the ordered pair 0, 4 is further away from the point 0, 2 than any other point that's kind of nearby it. It would only be a relative maximum because certainly there's other points in the curve. As x increases, the graph goes down and down and down, and then the distances between those points and 0, 2 would get larger. But in a region around 0, this point would be a relative maximum.